The National Electrical Code, or NEC, does not explicitly prohibit plugging multiple uninterruptible power supply, or UPS, systems into the same alternating current, or AC, source. However, the NEC does provide guidance on the installation and use of UPS systems in Article 700. There are several NEC considerations. Firstly, grounding. The grounding of all UPS systems connected to the same AC source must be properly coordinated to avoid potential ground loops. Secondly, overloading. The AC source must be sized to handle the combined load of all connected UPS systems, including their batteries. Thirdly, capacity. The UPS system should provide sufficient runtime and power capacity to support the critical loads connected to them. Fourthly, transfer time. The transfer time from AC power to backup battery power should be minimal to minimize the risk of data loss or equipment damage. There are also additional concerns. Firstly, power quality. If the AC source is subject to power fluctuations or outages, the multiple UPS systems may not be able to provide reliable backup power due to competition for the available AC power. Secondly, maintenance. Servicing or replacing multiple UPS systems in the same AC source can be challenging and may require coordination to avoid downtime. While the NEC does not explicitly prohibit the practice of plugging multiple UPS systems into the same AC source, it is generally not recommended. It is preferable to provide a dedicated AC source for each UPS system to ensure proper grounding, avoid overloading, and minimize power quality issues. If it is not feasible to provide a dedicated AC source for each UPS system, consider exploring alternative solutions. Firstly, shared battery systems. Install a central battery system that can be shared between multiple UPS systems. This provides redundancy and eliminates the need for multiple UPS batteries. Secondly, redundant AC sources. Provide two separate AC sources for the existing UPS and the new UPS, each with its own dedicated generator backup. This ensures that both UPS systems will have reliable AC power in the event of a power outage. Ground loops can cause a multitude of problems in electronic systems, primarily manifesting as unwanted noise and interference. A ground loop occurs when there are multiple paths to ground, creating a loop where current can circulate. This circulating current, even if small, can induce voltages in nearby circuits, leading to signal distortion and equipment malfunction. In the context of UPS systems, each UPS typically has its own connection to ground through the building's electrical system. When multiple UPS units are connected to the same AC source, they may create multiple ground paths. If the ground potentials at these points differ even slightly, current will flow through the ground loop. This current can then interfere with the sensitive electronic equipment powered by the UPS systems, especially if the equipment is also grounded at multiple points. To mitigate ground loops, it is crucial to ensure a single, well-defined ground reference point for all equipment. This can be achieved through proper grounding techniques, such as using star grounding configurations, where all ground connections radiate from a central point. Additionally, isolating the ground paths between different pieces of equipment can prevent circulating currents. This can be done using isolation transformers or by carefully managing the grounding of each device to avoid creating loops. Proper grounding not only minimizes noise and interference but also enhances safety by providing a low impedance path for fault currents, protecting personnel and equipment from electrical hazards. When sizing the AC source to handle the combined load of multiple UPS systems, it's essential to consider not only the nominal power consumption of the connected equipment but also the inrush current and the efficiency of the UPS units themselves. Inrush current, which is the instantaneous peak current drawn by a device when it is first turned on, can be significantly higher than the steady-state current. This is particularly relevant for UPS systems, as they often have large capacitors that need to be charged quickly upon startup or when switching from AC power to battery power. The AC source must be capable of supplying this inrush current without experiencing voltage dips or instability, which could affect the performance of other connected equipment. Additionally, the efficiency of the UPS system plays a critical role in determining the actual load on the AC source. UPS systems are not perfectly efficient, and some power is lost in the conversion process. This means that the AC source must supply more power than what is actually delivered to the connected equipment. For example, if a UPS system has an efficiency of 90%, it will draw approximately 111% of the power required by the connected equipment from the AC source. Therefore, when calculating the total load, it's important to account for both the inrush current and the efficiency of each UPS system to ensure that the AC source is adequately sized. Failing to do so can lead to overloading, voltage drops, and potential equipment damage. When evaluating the capacity of UPS systems, it's crucial to consider both the runtime and the power capacity to ensure that critical loads are adequately supported during power outages. Runtime refers to the amount of time the UPS can supply power to the connected equipment when AC power is lost. Power capacity, typically measured in voltamps or watts, indicates the maximum amount of power the UPS can deliver at any given time. To determine the required runtime, it's necessary to assess the duration of typical power outages in the area and the criticality of the connected equipment. For equipment that requires continuous operation, such as servers or medical devices, a longer runtime is essential. The power capacity of the UPS must be sufficient to support the total power demand of all connected equipment. This includes not only the steady-state power consumption, but also any peak loads or inrush currents that may occur during startup or operation. It's also important to consider future expansion when determining the power capacity of the UPS. As the power demands of the connected equipment increase over time, the UPS must be able to accommodate these additional loads without being overloaded. To ensure adequate capacity, it's generally recommended to select a UPS with a power capacity that is at least 20 to 25% greater than the current total power demand of the connected equipment. This provides a buffer for future growth and ensures that the UPS can handle any unexpected surges in power consumption. Minimizing the transfer time from AC power to battery power is crucial to prevent data loss and equipment damage during power outages. Transfer time refers to the amount of time it takes for the UPS to switch from using AC power to using battery power when a power outage occurs. During this brief period, the connected equipment is temporarily without power, which can lead to data corruption, system crashes, or even physical damage to sensitive components. To minimize the risk of these issues, it's essential to select a UPS with a fast transfer time. Modern UPS systems typically have transfer times ranging from 0 to 10 milliseconds. For most applications, a transfer time of 4 milliseconds or less is sufficient to prevent any noticeable disruption to the connected equipment. However, for particularly sensitive equipment, such as critical servers or medical devices, a zero transfer time UPS may be necessary. These UPS systems use a double conversion design, where the AC power is continuously converted to direct current, or DC, to charge the batteries, and then back to AC power to supply the connected equipment. This ensures that there is no interruption in power delivery when a power outage occurs, providing seamless protection against data loss and equipment damage. Power fluctuations and outages can significantly impact the reliability of backup power systems, especially when multiple UPS units are connected to the same AC source. Power fluctuations, such as voltage sags, surges, and frequency variations, can disrupt the operation of UPS systems and cause them to switch to battery power prematurely. This can reduce the overall runtime of the UPS and increase the risk of complete power loss during prolonged outages. Outages, on the other hand, can overwhelm the capacity of the AC source, leading to voltage drops and instability. When multiple UPS units are connected to the same AC source, they may compete for the available power, further exacerbating these issues. To mitigate the impact of power fluctuations and outages, it's essential to implement power conditioning equipment, such as voltage regulators, surge suppressors, and line filters. These devices can help to stabilize the AC power supply and protect the UPS systems from harmful voltage variations and transient surges. Additionally, it's important to ensure that the AC source is adequately sized to handle the combined load of all connected UPS units, as discussed previously. This will help to prevent voltage drops and instability during outages. Regular servicing and timely replacement of UPS systems are critical to ensure their continued reliability and performance. UPS systems are complex electronic devices that contain numerous components, including batteries, capacitors, fans, and control circuits. Over time, these components can degrade or fail, leading to reduced performance, increased risk of failure, and potential damage to connected equipment. Batteries, in particular, have a limited lifespan and must be replaced periodically to maintain the UPS ability to provide backup power. Capacitors can also degrade over time, leading to reduced efficiency and increased risk of failure. Fans can become clogged with dust and debris, leading to overheating and reduced performance. To prevent these issues, it's essential to establish a regular maintenance schedule for UPS systems. This should include periodic inspections, testing, and cleaning, as well as timely replacement of worn or failed components. The frequency of maintenance will depend on the age and condition of the UPS system, as well as the operating environment. In general, it's recommended to inspect UPS systems at least once per year and to replace batteries every 3 to 5 years. When multiple UPS systems are connected to the same AC source, servicing or replacing them can be particularly challenging, as it may require coordination to avoid downtime. In such cases, it's important to plan the maintenance activities carefully and to have backup power available to support the critical loads during the maintenance period. Shared battery systems offer a centralized and efficient solution for providing backup power to multiple UPS systems, eliminating the need for individual batteries in each unit. These systems typically consist of a large battery bank connected to a central power distribution unit. The power distribution unit then supplies DC power to the connected UPS systems, which convert it to AC power for the protected equipment. Shared battery systems offer several advantages over individual UPS batteries. Firstly, they provide greater redundancy, as the failure of a single battery in the bank will not necessarily result in a complete loss of backup power. Secondly, they can be more cost-effective, as the cost of a large battery bank is typically lower than the combined cost of individual UPS batteries. Thirdly, they simplify maintenance, as there are fewer batteries to maintain and replace. When designing a shared battery system, it's important to carefully consider the total power demand of the connected UPS systems, as well as the required runtime. The battery bank must be sized to provide sufficient power for all connected UPS systems for the desired duration. It's also important to consider the charging characteristics of the batteries and to select a charger that is compatible with the battery type and capacity. Additionally, the power distribution unit must be capable of distributing power to the connected UPS systems in a reliable and efficient manner. This may require the use of specialized power distribution equipment, such as circuit breakers, fuses, and monitoring systems. Redundant AC sources provide an additional layer of protection against power outages by ensuring that there are multiple independent sources of AC power available to the UPS systems. In a redundant AC source configuration, 2 or more AC power sources are connected to the UPS systems through a transfer switch. The transfer switch automatically selects the primary AC source when it is available and switches to the secondary AC source if the primary source fails. Redundant AC sources can be implemented in various ways, depending on the specific requirements of the application. One common approach is to use 2 separate utility feeds, each connected to a different substation. This provides protection against outages caused by failures in the utility grid. Another approach is to use a generator as the secondary AC source. This provides protection against outages caused by failures in both the utility grid and the local power distribution system. When designing a redundant AC source configuration, it's important to carefully consider the reliability of each AC source as well as the transfer time of the transfer switch. The AC sources should be selected to minimize the risk of simultaneous failures, and the transfer switch should be designed to switch between AC sources quickly and reliably. It's also important to ensure that the UPS systems are compatible with the redundant AC source configuration and that they can seamlessly switch between AC sources without interrupting power to the connected equipment. Neutral heating, also known as neutral overloading, can occur when the neutral conductor in an electrical circuit carries excessive current due to unbalanced loads or harmonic currents. In a balanced 3-phase system, the neutral conductor carries only a small amount of current, as the currents in the three phases tend to cancel each other out. However, if the loads in the three phases are not evenly distributed, the neutral conductor can carry a significant amount of current. Additionally, nonlinear loads, such as electronic devices and switching power supplies, can generate harmonic currents that flow through the neutral conductor. Excessive current in the neutral conductor can cause it to overheat, which can lead to insulation damage, fire hazards, and equipment malfunction. To prevent neutral heating, it's important to balance the loads on the three phases as much as possible and to use harmonic filters to reduce the amount of harmonic current flowing through the neutral conductor. It's also important to ensure that the neutral conductor is properly sized to handle the expected current load. The National Electrical Code, or NEC, provides guidance on the sizing of neutral conductors in Article 220.61. The NEC also requires the use of overcurrent protection devices, such as circuit breakers and fuses, to protect the neutral conductor from overloads. The best UPS, referring to a specific brand or model, is designed to provide clean and reliable AC power to connected equipment, protecting them from power fluctuations, outages, and other electrical disturbances. These UPS systems typically incorporate features such as voltage regulation, surge suppression, and harmonic filtering to ensure that the connected equipment receives a stable and clean power supply. They also include batteries that can provide backup power in the event of a power outage, allowing the connected equipment to continue operating for a specified period of time. The AV UPS, similarly designed to protect AV equipment, ensures uninterrupted operation during power disturbances. Integrating multiple UPS systems, such as the BEST UPS and the AV UPS, into an existing electrical infrastructure requires careful planning and consideration of various factors. It's important to assess the power requirements of each UPS system, as well as the overall power capacity of the electrical system. The electrical system must be able to supply sufficient power to all connected UPS systems without overloading any circuits or components. It's also important to consider the grounding and bonding requirements of each UPS system, as well as the potential for ground loops. The grounding and bonding systems must be designed to minimize the risk of electrical shock and to ensure proper operation of the UPS systems. Additionally, it's important to consider the environmental conditions in which the UPS systems will be operating. The UPS systems must be protected from excessive heat, humidity, and dust, as these conditions can affect their performance and lifespan. Proper ventilation and cooling may be necessary to maintain the UPS systems within their operating temperature range. The transfer time, as previously mentioned, should also be considered to prevent data loss and equipment damage. To address the specific concern of plugging the new AV UPS into outlets fed from the existing BEST UPS, it's essential to analyze the potential implications for the electrical system. While the NEC does not explicitly prohibit this practice, it's generally not recommended, as it can lead to several issues, including overloading, power quality problems, and increased risk of failure. Overloading can occur if the combined load of the BEST UPS and the AV UPS exceeds the capacity of the circuit feeding the outlets. This can cause the circuit breaker to trip, interrupting power to both UPS systems. Power quality problems can arise if the BEST UPS is not able to provide a clean and stable power supply to the AV UPS. This can lead to voltage fluctuations, harmonic distortion, and other electrical disturbances that can affect the performance of the AV UPS and the equipment connected to it. Increased risk of failure can result from the added stress on the BEST UPS, as it is now supplying power to two UPS systems instead of one. This can shorten the lifespan of the BEST UPS and increase the likelihood of a failure. To avoid these issues, it's recommended to provide a dedicated AC source for each UPS system. This ensures that each UPS system has its own independent power supply, minimizing the risk of overloading, power quality problems, and increased risk of failure. If a dedicated AC source is not feasible, other solutions, such as shared battery systems or redundant AC sources, may be considered. Article 700 of the NEC provides additional guidance on the installation and use of emergency systems, including UPS systems. This article covers topics such as wiring methods, overcurrent protection, and testing requirements. It's important to consult Article 700 of the NEC when installing or modifying UPS systems to ensure that they comply with all applicable requirements. In addition to the NEC, other standards and regulations may apply to UPS systems depending on the specific application and location. These may include standards from organizations such as the Institute of Electrical and Electronics Engineers, or IEE, the International Electrotechnical Commission, or ICE, and the Occupational Safety and Health Administration, or OSHA. It's important to be aware of all applicable standards and regulations and to ensure that the UPS systems comply with these requirements. Proper installation and maintenance of UPS systems are essential to ensure their reliable and safe operation. UPS systems should be installed by qualified electricians and should be inspected and maintained regularly. The maintenance schedule should include periodic inspections, testing, and cleaning, as well as timely replacement of worn or failed components. It's also important to keep accurate records of all maintenance activities. Regular maintenance can help to identify potential problems before they lead to failures and can extend the lifespan of the UPS systems. When multiple UPS systems are installed, it's important to coordinate the maintenance activities to minimize downtime. This may require the use of temporary backup power sources or the scheduling of maintenance activities during off-peak hours. In summary, while the NEC does not explicitly prohibit plugging multiple UPS systems into the same AC source, it's generally not recommended. It's preferable to provide a dedicated AC source for each UPS system to ensure proper grounding, avoid overloading, and minimize power quality issues. If a dedicated AC source is not feasible, other solutions, such as shared battery systems or redundant AC sources, may be considered. Proper installation and maintenance of UPS systems are essential to ensure their reliable and safe operation.